we learned how to construct group invariant representations to specific sorts of groups. That in that case, that was like one parameter groups. How to compute. So no, like our first family of nonlinear invariants. From arbitrary one parameter groups. And so immediate consequences of this very simple result is that we can extend it. This result can be extended, of course, to basically to higher dimensional abelian groups. And this is essentially using the same technique, because as long as you have things that commute, you still have this property that's the main property that we exploited, namely that if I have all these operators, like if my group is a group of transformations, if you think these transformations as matrices, if you want, the fact that the group commutes, the group is abelian, means that all these matrices commute, which means that they share a common eigenstructure. And so the group representation, the invariant representation, was, as you remember, really exploiting this eigenstructure. And in fact, it can also be extended to non-abelian groups. To non-abelian groups using a slightly more sophisticated techniques that we are not going to enter, right? So this is using group representation theory. For example, I don't know if people here are familiar. If I look at something of the form of the Peter Weil theorem, they gives us like the composition in terms of irreducible representations, and then you can use that also to build the same kind of invariant representation. But that's not for us. Not for today. Yeah. So the point is that we culminated the kind of the template that we obtained here using this route of looking at the kind of the Fourier transform of the group by something along the form that we had this kind of template of a representation that looks at certain linear transformation of the data and then remove the phase, right? Just because that's what the group is acting, right? The group is only acting on the phases. So if we kill the phases, we become invariant. Okay, so remember that V is what we can colloquially denote like the Fourier transform of the group. And so this analogy can be made completely concrete when you have the translation group in the domain. In that case, this matrix that we obtained through this Stone theorem was precisely the Fourier basis. But we also describe important shortcomings of this route, right? But I call this algebraic route. We describe a few of them. Is that symmetries are, let's say, straight or brittle criteria. Okay, and so basically they only describe very, very concrete construct families of transformations, right? In real life, nothing is an actual pure symmetry, right? Most of the things are approximate symmetries. And of course, in image, speech, they are very low dimension. So if you remember, we said, okay, if we only have a prior that the representation is invariant to this like a small number of degrees of freedom, how much are we gaining in terms of sample complexity? So the other question, of course, is like we need to understand how robust is this representation, the one that I'm describing here. To symmetries. Okay, so this we don't know. And the other one, of course, is that we don't know is that how much information are these Fourier invariants throwing away. Okay, so these are the two key questions, right? So, okay, we build these nonlinear features from understanding the, like the eigenstructure of the group. But then what happens with this representation as soon as we are slightly away from the group? And also how much information these nonlinear features are throwing away. Okay, these are the two questions. So let's try to start by the first one. And for this, we need to describe and formalize what we mean by near symmetries. Right? How do we go outside the group? So for this, we are going to introduce deformation models. And we are going to describe, formalize what we mean by geometric stability. Okay, so for this, we're going to fix ideas. Let's say that our input, now again, as usual, is a signal from define a small domain. And let's just forget about the boundary. Just put here, let's say, R. Okay, so this is just a thing that you have some image that makes okay, that would be like your X. Okay, but it's just defined on a, just for simplicity, I just think it as defined over a continuous grid. So before, that's the input. Okay, so before we consider so as a transformation, we consider like mappings that were of this form, that were from R2 to R2. Okay, so P of U was some A times U, right? That's the kind of transformation that we had before. Okay, so the degrees of freedom here, there are only 6 degrees of freedom, right? Okay, so now we are gonna go a little bit outside this model. So now let's generalize this thing, right? So the natural transition is that of considering this P, this transformation of the pixels to be linear or fine, we're gonna make it nonlinear. Okay, so now we are gonna replace it by a mapping that we call phi, that again goes from R2 to R2. And we just still asked for enough smoothness so that the whole algebra can still work out, right? So we're going to ask that this mapping is smooth and invertible. Okay, so we can still respect the algebra of transformations. Okay, and this is actually a differential. And we can write, if you want to think about specific way to think about these diffeomorphisms, you can think that these diffeomorphisms, they take the pixel and they move it. So essentially think about the perturbation of the identity, right? So they are just moving things a little bit, right? So it's the new location of the pixel is the old location minus some perturbation, right? So tau is again another field that goes from R2. And if you want to think about this like pictorially, think that this is your domain. And now I'm going to just prescribe, I have for every pixel, I'm going to move it somewhere, right? So this pixel is going to move here. This pixel is going to move here. This pixel is going to move here, right? So the displacement that I apply to every pixel is what is indicated by this vector field, right? But this tau. So that's the tau. And so if in absolute value if the the maximum displacement, if the elasticity of this deformation field is always smaller than 1, then we verify, and tau is let's say at least C1, right? Then we verify that this mapping is a diffeomorphism. Okay, it means that it's smooth and it has an inverse, and the inverse is also smooth. Okay. And so now we can basically say, use exactly the same formalism that we had last time. So now that we have this family of transformation of our domain, right? So how we can take these transformations of our domain and lift them into transformations or the signals that live on the domain. Okay, so now that we have this diffeomorphism, we can define a signal deformation as before. So we define this Newton transform image as like the new image at location at pixel u is the original image at u minus tau. Okay, that's really what you would imagine if you think that you take an image and then you apply a warp, right? And we can also, so again observe that. So if now I can think about this, that the mapping that goes from x to x tau is a linear map from L2 R2 to L2 R2. Right, so it maps images to images, and this mapping is linear. Okay, you can verify that very easily, and this is really just it's like a one-line proof. Okay, so we can write them. So we can write. Sometimes we are going to do it like this. We can write the deformation of some operator that is applied to x. Right. So this is a okay. Sometimes maybe later we might use this notation. Okay. And so one way to interpret this signal deformation is that we can think about this model as adding some sort of noise to the image. But this noise is not like the additive noise that you think, where every pixel value is perturbed by some corruption, as for example, when you take a picture with your phone at night, right? You have all these like noisy things on the image. So this is a noise, but it's instead of perturbing the colors, you are perturbing the locations of the pixels. Okay, so with this as geometric noise. Okay, so we add noise to the pixel locations rather than to the pixel values. Okay, this is just for you to, I mean, you to get like some good mental picture. All right, so that's our model. And so now we can postulate what do we want our functions, right, or representation to behave under this kind of deformations. This is the notion of the geometric stability. Right. So let me first ask the question, just to see if I get some inspiring responses. So the same way that we had before, that we introduced this like group of transformations, and we asked for representation to be invariant to this group. Does this notion make sense if we, you know, in the case where we have this group of diffeomorphisms? What are your thoughts? So could we ask now a representation to be invariant to the action of any diffeomorphism here as before? So think about what would happen if you have a representation that is invariant to any diffeomorphism. So think, for example, as an example, like digit classification, right? That's a very it's a very normal, it's a very interesting model, right? So let's say that you have a, you know, the class of ones. We have another label that is the class of sevens. Let's see. Okay, so KZ says the resultant orbit may be too small. No, the opposite, right? Think about whether you can relate these two images with a diffeomorphism. So can you actually map one to the other through a diffeomorphism that we wrote 5? Well, yes, right. That diffeomorphism is just a change of variables that you can invert, right? So you can keep, you can start moving pixels around, right, and try to move, like to deform the picture of the left to the picture of the right, to the picture in the right, just by applying, you know, a slight change of variables. So diffeomorphisms are vast, too large, right? So if I think about, you know, on the diagram, you could think that you have the space of all the diffeomorphisms, that is called actually the group of diffeomorphisms of the domain, that is R2, right? That's basically parameterized by all the mappings from R2 to R2 that are invertible and smooth. There's a lot. And there in the middle, somewhere hidden lurking there, there's a very tiny submanifold there that is just all those mappings that are affine. Okay, so this is like the Euclidean group, or like the rigid group. Okay, so these are the subfamily of diffeomorphisms. It's actually a subgroup of the group of diffeomorphisms that is generated by this affine motion, right? So we know And I think we can all agree that any function of interest that we want to learn is going to be invariant in the green region, right? Just because maybe the digit, right? Number 1, number 7, okay, that's, digits might be a little bit of a stretch if you start doing mirrors. But, more or less, if you translate, if you rotate, the digits don't change. But if you start stretching things around, then things is different, right? So here, we are happy to ask our model to be invariant, but certainly not invariant of the whole place, right? So somehow, what an idea that seems a bit more appropriate is to think that maybe I can define kind of a safe zone, right? I can, if things are not too far from a rigid translation, maybe I can still ask the model to be near invariant, right? So instead of having a all or nothing, whether either I'm asking things to be fully invariant or I'm not asking anything, maybe there's a notion that I can ask things to be near invariant. That's geometric stability. Okay, so let's try to formalize it and see what you think about. So we are going to define. So we define a notion of distance to the invariant. In that case, that will be the group of rigid motion, or the group of translations, if you want. Okay, so this is a in for sigma that is in the diffeomorphism group. We define the notion of distance to the invariance group, right? So let's say that we have in the case where I parameterize this phi of u to be u minus tau of u, right? Let's say that I can define this gamma of tau, right? That think about this as basically modeling how close is phi to being a translation. Okay. And for example, we can model this. We can express this desire with a quantity that maybe looks like this. I look at the gradient of tau. I look at the sup for the whole domain. Okay. So for example, so this, as you know, in the case where I have a translation, right? So in the case of translation, what is tau, right? So for fact, phi of u the translation, then tau of u by definition is u0. So the gradient of tau is 0 for all u. Right? So this quantity, so what I have is that phi of tau is greater than 0 for all tau, and for translations, and is 0 for translations. Right? So de facto, you can think of this notion as this quantity as measuring like the distance to the translation group. So now we can ask the question, we can say that we hypothesize, we postulate that target f such that for all x and for all tau, f of x minus f of the deformation of x, they are like the distance between these two images is of the order of the deformation cost. Okay, so this we can call it. We can also call it here like the deformation cost. Okay, so we are saying that translations cost nothing, but the more you are far from a translation, the more you pay. And so here, what we are saying is that the function, right? So the f is stable to the deformations. Okay, so if I have a deformation where this gamma of tau is very, very, very small, meaning that maybe the thing is not an exact translation, but it's very close to being a translation, then we are our function to be almost constant, right? Like not to change too much. Okay, and this notation, sorry, means that the constants might depend on x, but not on that. Okay, this so when I write this approximate control, right? That's what I mean. Okay. So is there any question about this definition? Does it make sense to you? Yeah. Okay. So let me just as a remark. So we define this like for the translation group. We can use this deformation cost. That, as I said before, it's the sup over u of the gradient of tau of u. But this can be extended to other groups as well. For example, the rigid motion group. Okay, so this game that we had, where we are in this point here, right? Like in this diagram here. Actually, so you see it here. Okay, great. Okay, so if I'm in this diagram here, if I replace this like a region, like the red invariance group by maybe like a different group, I can still come up with a relevant definition of the distance on the group, like the distance to this invariance group. Okay, but that's not important for us. All right. So if our target function is has this property, right? So we postulate that the function we want to learn have this property. The natural question is, how are we going to ask, or how can we leverage this assumption, right? This is an assumption, and so we can define like geometrically stable different representations. Like using the natural, I guess, as we would natural expect, right? So we ask that for all x and for all tau, we ask for representation phi to satisfy exactly the same property. Right? X minus phi of L of x to be of the order of the deformation. Again, so of course, this generalizes translation facts. Okay, because the translation invariance, of course, is when you plug here tau, a deformation that is constant, the right-hand side is here. Okay. Okay. Very. And let me also mention that there's also a natural extension local geometric stability, right? So the local geometric stability is that in some applications, we might not be necessarily interested in having a representation that is invariant to the whole translation group, but only to small translations, local translations. That is something that we can also totally accommodate in this definition, right? So, for example, we are interested. Okay, so we can define a deformation cost. That is the thing that we had before. And then we can add a term that maybe says, okay, I'm going to have some parameter. Let's call this parameter actually just do it like this now for now. That I just say, okay, I just look at tau. Okay, so this is basically what is this thing telling us? This is the distortion, right? And this is the displacement. Okay, so if I have a change of variables that moves things very far, I still want to be able to detect it, right? I don't need to be invariant to all these things, right? So this is this controls. Okay. Okay, so now there's a natural question that yes, there's a question, Victor.
Yes, Juan. So in this geometric stability, you are not saying nothing about you're not saying anything about the tau transformation. Could this be as big as you want, so that the gradient be
okay? Yeah, that's a good question. So of course, if the right hand side in this term here, right? If the right hand side is very large, this hypothesis doesn't see anything. It's not meaningful, right? So you should always interpret that this hypothesis is useful. It's carrying information when the right hand side is small. And so that's why I come back again to this picture here, that you can think about this deformation cost as measuring some kind of like a distance to this orbit, right? To this like a rigid translation group. And so it's going to be very informative when you're nearby this man. Although outside, it doesn't prescribe anything. Yeah, you're correct. The intuition is correct. Okay. So a question here for you, maybe for us, is that let's try to combine this hypothesis with the representation that we learned about last week, right? So R, the Fourier invariance, like the representation that we had before, that is just the absolute value of the Fourier transform, are they geometrically stable? Okay, so that's what we can check here. All right. Okay, so for this, we can maybe try to construct a counterexample that will hopefully illustrate that this choice was maybe not the best one. So for this, let me just introduce this image. Like, let's consider and we can do it in 1D, right? Just pick, so U in R. Okay, so we just look at the 1D example. That is X of U, that is some window H that I modulate with a certain frequency. Okay, let's try to see what this is, right? So H of U, H is a low pass. Okay, so let me just try to illustrate this in a picture. Right, so I consider U to be here, to be real, and then I consider like a window. That is this H of U. Now what I'm doing is I'm just multiplying, like modulating, right, this window by sine and cosine, right? And here I'm just looking at the complex case, but just think about this, that you are just constructing a function that really in the real part looks like this. Okay, so there are two parameters here. Okay, so the parameters are the bandwidth of the low-pass filter that we can call sigma, and then the other parameter, so basically two parameters. So two parameters, sigma, that is the spatial bandwidth, h, and then psi 0, that is the oscillating frequency, the central frequency. Okay, so that's our model. It's like a little wave that is on an oscillate. All right, and now we are going to consider, so that's our signal. And now let's consider like a very well chosen deformation. So consider warping of the form of x of u, that is just going to do x of 1 plus epsilon times u. Okay, with epsilon very, very small, right? So it's basically doing a very slight dilation of the domain. Okay, so now let's compute. So now let's relate, or let's compute phi of x and phi of delta of x. Okay, so remember that this is just like looking at the Fourier transform and just looking at the absolute value. So we need to remember, I think on Tuesdays, Sebastian went a little bit through some basics of harmonic analysis. So we need to use just a little bit of that. Okay, so we need to remember how to compute the Fourier transform under a dilation. Change of variables, that is a dilation. So let's do that. So if I look at the Fourier transform of the dilation, if you remember, this is a 1 plus epsilon, the minus 1, times the Fourier transform of x applied at the inverse Fourier, basically where I invert the sense of the dilation, right? So if I dilate by some factor in the spatial domain, I compress in the Fourier domain, right? In the inverse direction. Okay, so the Fourier transform of this model at frequency psi, I can relate it to this model. And of course, now we can use the definition of our function, right? So remember that we call that x of u is of the form h of u times something like this. So what is the Fourier transform of a modulated window? If you remember, this means that the Fourier transform of x, xi, is the Fourier transform of h at the translation in frequency, right? So modulating, so this is just the case. Modulation in spatial domain corresponds to the translation. And you know that this also goes both ways, right? Like if I translate in one domain, I modulate in the other, right? That's another property of the Fourier transform. So by putting these things together, the Fourier transform signal, by replacing things, is 1 plus epsilon minus 1. The Fourier transform of our Lopez window, H, that is evaluated at 1 plus epsilon minus 1 of psi minus psi. Okay, and so now we can plot, we can try to see what we get. So let's try to plot the two signals of interest in the Fourier domain, right? So now we are going to look at the Fourier domain. So here's our initial window, so that the Fourier transform of x. So it has a central frequency, psi 0, and it has bandwidth that is basically the inverse of the other one, right? And maybe here I should have said, just by simplicity, allow me to do the following, doesn't really matter, right? Minus 1. Okay, so now this parameter becomes sigma. Okay, so that's my x, and now let's try to rate what I have here. So now in this function, right, I have a bandwidth. So what is the bandwidth of this function, right? So I have applied a dilation. I have applied a dilation in the spatial domain, which also translates into like the inverse dilation in the frequency domain. So the bandwidth has moved, right? So from being this sigma to a function that has moved, like the bandwidth has been expanded by sigma times 1 plus epsilon. And also, what is the central frequency, right? If you look at this formula here, right, the central frequency, we can see that it also has moved, right? So now the central frequency is psi 0 times 1 plus epsilon, right? And the bandwidth has also has moved, right? So if I just put everything together, now I have the Fourier transform x that has two parameters that now become here becomes like sigma times 1 plus epsilon. Okay, so basically I had two parameters before, the bandwidth and the central frequency, and when I apply a dilation, these two parameters evolve, right? And they have been multiplied by 1 plus epsilon. And now we can see what happens, right? Let's argue what happens. So now we need to compare, we need to look at we need to compute the difference, right, between absolute value of x hat minus the absolute value of delta of x hat. So basically, we need to look at the norm, like at the Euclidean distance between these two signals after removing the phase. But what happens when the supports are very far? Right, when I compare the Euclidean distance between two signals that have disjoint support, right? So we actually would like this to be small, right? So basically remember that we would ideally, if this representation was geometrically stable, if epsilon was very small, so remember that here, so something I didn't say, right, is that if I look at this corresponding model, right, tau of u, right, is epsilon times u, which means that this gamma of tau that we described is just epsilon, right? So the question is that why is this thing of the order of epsilon? Okay, so is this true? We need to verify, or we need to whether this thing is true. Actually, there's something I got. Yes, I realized that there's something I said wrong before, but we need to verify whether this property is true independently or uniformly over X. Okay. So now I realized that before I was being a little bit too brutal when I said that this thing was actually constant might depend on X. No, that's actually not something I want to say. Constant might depend on the log of X. Okay, sorry about this confusion. Okay, so what I mean here is that now we need to verify whether this is true independently of the choice of the function of X, right, in our model. And this has to be small with respect to epsilon. But let's look at this diagram here. When can we, if you look at this picture, what happens when these two signals with these two windows are nearly disjoint? Well, that's a problem, right? So in other words, basically what happens is that when the difference between the two central frequencies, so when 1 plus epsilon psi 0 minus psi 0 is much bigger than like the sum of the two bandwidth, right? That sigma h plus sigma h 1 plus epsilon over 2, right? What we are saying here is that with the difference between these two central frequencies, right? When this difference is much, much, much bigger than the sum of the two bandwidths, then X, the Fourier transform of X and the Fourier transform of the deformations have nearly disjoint support, right? Like the two windows, right? So we have in this picture, we had one window here and one window here, right? But these are completely disjoint, which means that the Fourier transform, like the difference between the two, is of the order of the sum, right, of the two, right? Is of the order. So you are basically looking at the Euclidean distance between two vectors that are orthogonal, right? So which means that this is basically of the order of the sum, or like the one of the two, right? Okay, just because the difference between two vectors that have disjoint support, like being disjoint support means that they are orthogonal. And so there's no way that difference of two vectors that are orthogonal is going to be small unless the two vectors are small at the beginning. Okay, so which means that if I have this property, if this thing is satisfied, then there's no way that the right-hand side here, right, that this thing is going to be true, right? Because I want, that basically means that for every epsilon, even if epsilon is very small, so let's try to see what this inequality gives us, right? So here, if I see what happens, I get epsilon times psi 0 is bigger than basically sigma h. If epsilon is very small, that doesn't matter, right? It's like of the order of this property, right? So so it means that even if I choose epsilon that is very, very small, there will be always a choice of central frequency, right? If psi 0 is sufficiently large, these things is not gonna work, right? So then I'm not gonna be able to. I'm not gonna have this stability, right? So what it means is that like the conclusion, right? So then, so if this happens, then the difference between phi of x minus phi of delta of x is of the order of x, right? So even if epsilon, right, is very, very small, right? So there's no stability. And here now you see why, you know, I mean, obviously, what I wrote before was obviously not true, right? Because you don't want to allow your stability constant to depend on x, right? Because of course here what you see is that the difference between the two functions, right, blows up the more you go into the high frequencies, right? So the reason why you have this problem, the difference between these two functions is not small, is because if you push information to the high frequencies, right, like the high frequency information is unstable. Stable through deformations. Even if the formations are near translations. So here we have really isolated the core problem, right? Is that yes, if I look at the translation, I know that any Fourier coefficient of the signal, even if it's like a very high frequency coefficient, strictly speaking, is going to be, if I look at the modulus of this, right, that's going to be it's going to be an invariant, right? Like the translation group is not going to move frequencies. It's not going to move information throughout the frequencies. But as soon as I have something that is not an exact translation, that is just something that is barely a translation, it's just tiny epsilon, very, 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 very small, then everything starts to shift around, right? Like all the information is just floating, it's like just moving from one frequency to the other, right? So these things are no longer invariants. And no matter how small the epsilon is, there will be always some frequency that will become unstable. Okay, that's what it's trying to capture here in this big conclusion. Okay, so that's an important takeaway from this example. And so this is really now we need to basically go back to our drawing board and maybe try to figure out a better way to build invariants that doesn't have this problem. Any questions about this example? This is an important example that essentially invalidates everything we talked about last week, right? Because this idea that you can build invariants by understanding kind of the Fourier transform of the group, that is something that you can use for translation, but you can use for like rotation, like the permutations, etc. This is like an algebra construction, so you get invariant to what you are asking for, but it's not something. It's a brittle property, right? It doesn't give you any robustness to what happens just outside the group. Okay, so this is like now we are going to really take a completely different approach, where we are going to build a different invariant, a different family of invariants that has this stability concern from the beginning. Okay, so if there are no questions, I will go on. if you want, we can take a break of 2 minutes now that we're gonna continue here. Okay, so yeah, maybe we can resume in so it's going to be for you, it's going to be at 5 p.m. right, in 2 minutes.
May I ask you something, John?
Of course.
So I'm struggling a bit on understanding this. So this x of u,
Yes.
what it is? What is it really?
X of u is in this example that was just like a signal, like a think about like a real function, like a function goes from R to R. Okay, so
So when you parameterize it with this mode, no, with this phase and
you mean this in this definition?
yeah,
right?
exactly, yeah.
Yeah, so the X of u is this like purple thing. Like think about like this little wave that is oscillating.
Mm-hmm.
Okay, and so so this thing about this would be your, if you think like a speech recognition, that could be your input. And so you want to build a representation for this kind of like a time series that is not only translation invariant, but it's also something that if I just apply a very small, like a slight deformation of the domain, I don't want my representation to be completely different, right? So I would like the representation to be, if I deform the domain a little bit, the representation should change a little bit. And so the conclusion here, yes.
So the thing is that the fine details of these
Yes.
the input data are not preserved, no?
Well, that's a good, yeah. That the point is that if I look at
or they are deformed in a way that you don't like.
That's the key. That's the key diagram, right? So if I think about how this little, example, like it's a little wave that I constructed, right? So if you see what happens as you apply a slight warping of your domain, the high frequencies are gonna move, and the amount by which they move, the key point is that it's not just proportional to epsilon.
Mm-hmm.
It's proportional to sigma 0 times epsilon, psi 0 times epsilon. So like the more high frequencies I have, the farther they are going to translate. And so that's what creates the whole problem, right? Is that for any, even if I choose epsilon very, 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 very small, like I don't know, 0.111%, 0.001%, there will be always some bandwidth, some psi 0, for which this difference is going to be amplified, right? It's going to be large. And so there's no way I can have something that is uniformly stable to deformations, uniformly over the choice of high frequency.
Yeah. Okay.
So that's the right. So that's the thing that we are going to try to fix now. Let's see how we can maybe remediate this problem. All right. So I guess that the key, if I had to, to describe like the punchline, right? Like we're going to now spend some time developing an alternative thing, but basically the punchline of what will come next is that rather than attempting to build invariants in one shot, which is basically like a single layer, as we did before, we will build it progressively. Okay, that's the kind of the punchline that we are going to develop today. So think about, again, this picture of the orbits, right, that we had before. This X, And here we have these, translation, like the unitary transformations of x, right? Like this T of x. Okay. And so now we are going to try to build a representation, right? So instead of actually trying to construct a representation that is constant along the orbits, we are just happy if this representation is very smooth along the orbits, right? So the derivatives, like that, the changes that happen along the orbit are small. Okay, so I can maybe manifest it by saying that my representation as I move along the orbit. So let me just now introduce some notion of distance along the orbit, right? So let's put here some v, right? So the v, think about this like if you have only one parameter, the v would be like the time, right? Like I can travel far, like I can travel a certain distance along the orbit, and v is something that depends on the distance. So what I'm trying to express here is that I could just maybe start by trying to build a representation phi, such that this thing is basically of the order of 2 to the minus basically this is a this is of the order of v, maybe with some with some units, right, that I can maybe just build here. Let's put here like a constant just to make it more specific, right? Some 2 to the minus j times v. Okay, so it means that, in other words, if v is much more than 2 to the j, right, then these representations should be close to each other. Okay, so this j, 2 to the j is kind of like the scale, right? It's like if things that are, if I move if I move along the orbit much less than certain nominal scale, 2 to the j, then the representation should not change too much. So this is another way to think about it, right? Is that this is equivalent to some form of a derivative being small, right? So if I think about this problem, I can very informally put the normal b in the denominator and say that this thing is basically upper bounding by 2 to the minus j, right, for all. So this, the left-hand side here, right, this looks like a derivative along the orbit, right? So basically, I'm just re-expressing the fact that when I move along the orbit, I don't want to have big changes. The derivative has to be small. So how can we ensure that our representation is smooth along the orbit? Well, that's something very easy. We can just explicitly smooth, right? So we can create local invariants. Here, when I say local, it's basically because it's relative to the scale. By smoothing along the orbit. Okay, so in more concrete terms, I can define the derivative of this form, right? I can just say this is j, then I can put the group, I can put a window, that just averages the information of X, right? And here I can just put and here H can be any positive window, right? Like a kind of a weighted window. Okay, so basically here, the only thing I'm saying really is that I have like a weighted average of the, I'm just doing a weighted average along the orbit of the group. So just to make sure that here we are all happy, right, is that in the case of the translation group, this is nothing else than saying that I have a integral over R, if I just do it in 1D, of some window that is this parameterization of a V, and then here what I'm just saying is that this is just X U minus V D in coordinates, and this is just a convolution. And this is a low-pass filter. Of course, if I change the scale, right, if I make J very, 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 very large, I converge to the total invariant, right? But if I fix J, I can just see it as some kind of like a low-pass filter. So this is it seems like a very convoluted way to just introduce a low-pass filter, right? But in fact, we can verify that this is, so this is in a sense a more like a humble, in a sense it's like it's a much more humble construction than what we did before with the group and the Fourier transform and the Stone theorem. But yet it has a property that the other ones don't have, right? Is that in fact, this low-pass filter is stable beyond the orbit. So basically, this low-pass filter that is constructed just in the orbit, in fact, it gives us stability for free. Okay, and so what do I mean by this? Is that if I have this operation, phi of x, that is just it's a representation that in the case is it's linear, it's just a convolution with a low-pass filter, satisfies for all x, it's unitary, for all tau, the fact that this minus the low-pass filter applied to the deformation is small. It's controlled by a constant that doesn't depend on x nor tau times the absolute value, like the absolute largest displacements times 2 to the minus g. So before we say a few words about how to prove that, we can try to understand intuitively what this is telling us. If I look at an image, a signal, and I just apply this low-pass filter, I'm basically killing the high frequencies, right? I'm just keeping the low frequency information of the signal. So what this result says is that low frequencies are stable. Right? In other words, and so this should also relate. This should resonate with the previous example we had, right? Is that we, in order to kind of break this Fourier modulus, we had to see, basically to look at data, input data, that was going into the high dimensions, sorry, into the high frequencies, right? So it means that essentially, if we don't do this trick, then actually there's stability, right? So that's really like the key problem is high frequency, right? So just so that we can get a grasp on how to prove this kind of results, right? Just I'm going to do like a very simple like a proof idea, right? I mean, here first observe like there's one simple observation that then makes the proof easy. Is that let's look at this object here, right? So let's first look at what we have here. So phi is a convolution with a low-pass filter. And I told you that this operator of the formation is linear. So what are we looking at in this green box? That this mapping that goes from X to this complicated thing is what? Is linear. Right? Because I'm just I'm making like a difference between the first term here is obviously linear, right? By definition of phi. And then I'm composing two linear operators, right? Phi and alpha. So it means that if it's linear, then it means I'm basically just asking the question, right? So I can think about this object, right? So I can think about phi of x minus phi of delta of x as some operator. We can call it a of x, right? The dependent tau. So I'm just asking you, when is this operator? So actually, because remember that I have here this constraint that is the f1. So basically, I'm just asking you, when is this operator going to be as the property that for any x, the norm of the output is more than 1. So this is really just controlling the operator norm of eta. Okay. So the only, of course, the only like maybe potentially non-standard thing is that these are operators defined over infinite dimensional space, right? So these are infinite dimensional things, but that's the only. If you once you have in mind that you are just manipulating very large matrices, the proof is really just like in spirit is just computing the bounding the norm of a matrix, the operator norm of a matrix. So first we need to understand, we need to compute this matrix, right? And so here we use like the technique to bound the operator norm. Now is what's called a Shor length. Okay, so we need to first, when we think about linear operators defined over infinite dimensional space, we need to write them in what's called like an integral operator. Okay, so here we need to think that a of x, if we express this in coordinates, right? So if we look at what happens at coordinate u, you can always, because it's a linear operator, we can write it as in terms of what's called a kernel. Right? Like these are kind of like the entry, right? If you write a matrix in the entry, right? So these are kind of the entries of the matrix. Okay, that's x of tilde. Okay, so we need to compute what are the entries of this matrix. So the Shor lemma first, like let me just first state what the Shor lemma is, right? So if I have an integral operator with a kernel k, Then the norm of A is upper bounded by the max in the sup over U of basically integrating over the rows matrix or integrating over the columns. Okay, so if I have a matrix, the operator of a matrix, I can upper bound it by some kind of like a mixed L1, L infinity, right? That's what this should end saying. So now we just need to compute. We need to compute K of U in our case, right? So let's do that. So remember, recall A of X and U. So A of X is X convolved K minus delta of X convolved K. Okay. So let's go step by step. So we know that by definition, yeah, this is what we call finiteness. The integral of B times J of U minus V. Okay, so a convolution obviously is always expressed as an integral operator, and the kernel of a convolution, right, is really this this object agent, right? It's already directly the filter. But in coordinates, now I think remember what is tau of X, U. This is just X of U minus tau of U. So now we need to compute phi of L tau of X. Composing the deformation with the low pass filter. So let's justify the definition. X of B minus B times V D. Okay. So remember that look at what what we need to understand, right? What we need to write is the kernel of an integral operator. Let's look at this formula. Okay. We need to express everything as an integral, like anything times the input integrated over the original domain, right? So here, this form, we have it here, so that's kind of okay, right? Because it's in this form. But if you look at here, that's not in this form, right? Because instead of having integrating over B here, we are integrating over this weird thing. So we just need to remessage this a little bit. So how can we do that? That's basically the only trick that that is available to us in this context. That is to introduce a change of variables. Okay, so we are going to introduce a change of variables where now this is going to become d tilde. Why can we do that? Why is it okay to do that? Precisely because this is a diffeomorphism, right? So there is, I can invert, right? So this is I can write it as x of b times xj of u minus v plus corresponding inverse field, right? So if I have that b tilde is equal to b minus tau of b, then b is equal to b tilde minus beta of b tilde, right? For b tilde is kind of the inverse deformation of tau. Okay. And I know that I can always do that, right? Because I have a different one. So this now becomes beta of b times the determinant of the Jacobi, right? Of the change of variables, which is now b. Right. So now I'm almost done because now I can just look at the kernel of phi of x minus phi of alpha of x and u. Now I can just write it as integral of x of b times the convolutional part, which is u minus b, minus this new part that we have just developed, that is fj of u minus b plus beta b times this change of variables. So in other words, so the kernel of the operator is just hj of u minus b minus fj of u minus b plus beta of b times this term. Okay, so now we just need to play the assumption, right? So we need to now go back and somehow show that this thing, right, is upper bounded by something that is proportional to the maximum displacement times 2 to the minus j. So when we look at this problem, right, how can you show? Basically, now we are in the business of trying to show that this kernel is small, right? In the sense that these entries are small, so that when I integrate them, I'm gonna get, basically I can use this. I need to show that this term can be made small, like of the order of 2 to the minus j times the larger displacement, as well as this term. And so now there's only one last idea, right? So basically, last idea is that now leverage, like the use the smoothness, right, of hj, okay, plus tail. Yes, in other words, the term that is causing me some problems, right? B minus b plus b. I need to do Taylor, right, around u minus b, right, because that's the term that we have here, right? So you are going to write it as xj of u minus b plus what? Plus the derivative, right? So plus hj prime of u minus b times, right? Plus some term that is going to be small, right? That is a control. That is derivative is actually and so if you remember that, recall from the definition of the Lopez filter here, right? So x, right? So so xj, right? So we call that xj u is 2 to the minus j, h of 2 to the minus j, right? So the bigger j, right? So small j, j, and if you make j bigger, what happens with this filter, with this window, just becomes more dilated, right? Like this is large. So what happens as I make this thing more and more and more stretched? What happens with the derivative? It just it becomes
It
much
goes to
smaller,
zero.
right? And so so then what you see here, right, is that the derivative is of the order, right? So the derivative picture of prime, right, is of the order of 2 to the minus 2. Okay, which means that if I look at this Taylor decomposition, right, this error, basically this is what kind of this term here is killed by this term here. So the most dominant term is the first order term, right? In the first order term, this is where you see that there's a dependency on 2 to the minus j. Okay. There's of course, now you need, there's a few more details that you need to verify that you can integrate these like a short lemma, right? That you can integrate along the rows and the columns, but the gist, the essential idea is really this, right? All right. So again, this result is just the verifying, right? So this is just verifying our intuition that low frequencies are stable to deformations, to small deformations. Okay, but of course, low frequencies like low pass filter, right? However, the low pass filters, right? Low pass filter of the form throws all high frequency information, all high frequency information. So obviously, we don't want to do that, right? We don't want to just say, okay, I have this linear operator that is fantastic, that is just looking at the low frequencies. That's what you want to use for classification, right? This is just completely throwing away information that is completely critical for classification, right? And I cannot maybe show it here, on writing, but maybe you can try to convince yourself that if you try to, let's say, read a book and you put yourself glasses that are blurring your vision, you're not going to be able to read anything, right? So your recognition engine needs to have high frequencies, right? Just to recognize text or anything that you want to see, right? And this is like this information is critical for recognition. Okay, so we need to do something else, right? But another thing that we know, right, is that maybe here I can just give you the gist of it, right? Is that there's no other, however, another problem, right? Are there, so that this just the question is, are there other stable linear operators? So the low pass filter is stable and it's nice, it's easy to understand, it's linear. So are there other linear stable operators that maybe do not throw the information that we see here above? So stable plus linear, are there more? Well, here I'm going to give you like a slightly hand-wavy argument that there are no more, right? That there's nothing else out there that is stable and linear. Maybe I can just really, again, hand-waving a little bit. I can say, well, if I know that for all v, phi of v, here like stable or like in particular invariant. Okay, like let's start with translation invariant, which is like a which is a stronger condition than. So in particular, if it's stable, it's translation invariant. Right? So like translation invariant are okay. In particular, they have to be translation invariant. Right. So if something is translation invariant, right, it means that this is equal to phi of translation. It means that phi of x is also equal to the average over the group, right? And here I'm just being again very sloppy, but I guess that this is the idea that you get the idea, right? I can integrate over the group. Right? Just because if this thing doesn't change, right? I can integrate it over the group. But now, if this thing is linear, I can also write this as phi of 1 over g, the average of the group. Right? By linearity, I can swap the order of the operation and the group. Right? Which means that this is actually, this is the signal average, right? Okay, if I just look at an image and I just replace it by the average over all the translated version of the image, right? So this is what you get here is just the integral over x of v, right? In the case of translations. One for the size of the group. And so basically that the point is that the conclusion is that the only linear invariant operator is the average. Okay. So as a corollary, is that invariant representation that captures high frequency must involve a nonlinearity. Okay, so we need to go nonlinear. Okay, and for this we are going to now we're going to see how we can incorporate nonlinearity, and for this we're going to finally introduce the wave-based scattering representations. Okay, so we are going to see how we can complement this low-pass filter, and how we naturally need to use a nonlinearity to do that. Okay, so for this, I'm going to define a function here. It's like phi, the bandpass function that is just integrable. So let's say L1. And I'm going to think that I have a domain that is S, right? S equals 1 for time, S equals 2 for images. And I'm just focusing on these two cases, right? Doesn't really, the rest of the argument doesn't change too much. So what I mean bandpass here, it it means that the function, that this little thing needs to oscillate, right? And we can formalize this by saying there's at least one vanishing moment. So in other words, the integral of phi of u du is 0. And let me also ask the phi to be well localized both in space and in frequency. Okay, and so let me just start by introducing two very kind of canonical or simple examples that hopefully give you the right picture. So that's like two canonical examples. Hard wavelets. There's a hard wavelets. The corresponding phi looks like a way that has like basically two parts, like a positive and then a negative, right? It's a little wave. In that case, you can verify that it has zero mean, right? So the average of this wave is 0. And indeed, these wavelets are very popular across many applications. There's another example that even though it's not formally true, but hopefully will also give you the right picture, that is this family of what's called Gabor wavelets. Okay, so here I construct phi of u from basically the previous example that we had shown before, which is like I take a Gaussian window, H, and I modulate it. Okay, so these are just maybe put here a Gaussian. Okay, so let me just put here a asterisk because strictly speaking, not wavelets since they are not exactly 0 bit, right? So this is not 0 in general, right? And maybe it's a good exercise for you to show why. Okay, but doesn't matter. I mean, I guess that for you the picture should be the same as before, right? That I have some wave. So I think that it's like I have an envelope that is like a Gaussian window, and then I just apply some modulation. Okay, and so now the question is, okay, we have this wave. How can we use these waves to extract interesting information from a signal of interest, X? Okay, and so whereas Fourier transform what they do with Fourier transforms is that you take your signal and you write it, you express it as a sum of frequencies, right? You in terms of a linear combination of sine and cosine. So here we are going to change a little bit the perspective, and so where Fourier transforms express signals as linear combinations of sines, basically in terms of frequencies, wavelet transforms use scale instead. So instead of frequency, we're going to use scale. So what is that? So I define, given this model wavelets, that's also called like a model wavelet. Okay, so I'm going to define ij of u to be 2 to the minus j, the original model wavelet, times 2 to the minus j times. Right, this is in 1D, dimension 1. And if I have more dimensions, right, in 2 dimensions, for example, I can define it by introducing some, here I need to normalize it. In terms of taking the model wavelet and applying a dilation and also a rotation. So I'm going to take my model wavelet and apply a rotation. So just to give you the picture, right? So the picture would be that, you know, let me draw the picture in 1D, right? So you would have some original wave. So just going to draw it like this. So from this wave, I generate a family of waves, right? So from this, I generate a collection of wavelets, right? And so the first one would be maybe something that is very small. Then I have something that is a bit bigger, etc., etc., etc. Right? So you can see that this domain is proportional to 2 to the j, right? And the amplitude is proportional to 2 to the minus j. Okay, and so in the case of 2D, think that the operation that you do is like you can think that you have some, you know, I'm drawing this thing, but imagine that you have a wavelet, right? That has some support like this, right? Maybe it has some oscillation, right? So think that you have a wave, that you have a sine and cosine, but they are oriented along a certain direction. And so whenever you apply a rotation, right, you are also going to be able to shift. Right? You can place the wavelet according to different orientations, and then you can also make it bigger or smaller. Okay, so these are the 2 parameters. And so notice that there's a normalization factor, right? So this normalization that you see here, right? It's here just to make sure we use L1 normalization. So basically the L1 norm of the filter is the same as the model wave for all j and for all. Okay, and so this is like a technical condition that is necessary, that is needed for the representation to be well defined, right? As a representation that preserves the energy that we care about. Okay, and so in what sense this is useful? In the following sense, right? So once we have this collection of all these wavelets, we can define what's called Littlewood-Pelly wavelet transform. Which is for x that is an input that is square integrable in our domain. So remember that this is either R1 or R2, right? We define the wavelet representation as the collection. First, I compute the low pass filter at scale j, And then I complement it with the wavelet filters, the wavelet filter at any possible scale and orientation. So sorry, the scales that are at most j, and the filter and the orientations that are in some kind of a discrete rotation. Right? So this is like a discrete rotation. Right. So for instance, I take my different angles, right? In 2D, I have maybe, I have from 0 to 2 pi, and I discretize it into, let's say, 10 angles, and I have one of the wavelets for each of these angles. Okay, so basically I map a signal x to a collection, but actually to an infinite connection of signals, right? So the index here, right? So basically if I think about this index, right? So like if I pack both the scale and the angle, the coefficient, so this lambda belongs to basically all the possible integers times this scale j that belongs to minus infinity j, and then angle also becomes to this t. Okay, and so why is this useful? So here we are just taking a signal and expressing it as a convolution where we are creating all these convolutions that extract information at different scales on orientations. And this is what justifies, so we are going to see now why we have this normalization, is that now we have a very simple characterization of the energy that is preserved in this representation. Okay, so this is a theorem by Little that says that if exists delta that is bigger than 0, such that for every frequency we have the following: 1 minus delta is smaller than the absolute bar, the Fourier transform psi squared plus 1/2 the sum over this, let's call this lambda for the main of the Fourier transform of the model wavelet evaluated at all these possible locations. This is more than 1, right? So this is kind of a design. It's a property that says that for every frequency, if I look at the following sum, this is always sandwiched between 1 minus delta and 1. So if this is true, then for x equal 2, then the norm of x is controlled in the wavelet representation, right? So basically now this is the same as the norm of x L2 of omega times squared. Right, to remember that the norm of this wavelet transform in the scattering domain, sorry, the wavelet domain, is just defined as the norm of the low pass plus the sum lambda of x. Okay. Okay, so in other words, energy is preserved in the wavelet domain. Okay, so far this is not really saying, it's not saying anything too fantastic, right? I mean, we are just saying that we have a signal, we compute this filter bank, and we can collect, from looking at all these coefficients in the wavelet domain, we can collect the energy. Like we can basically reconstruct the X original, right? So the filter bank is very redundant, right? So you are basically going from, if I think in terms of an image, right? So we have some input X, and here we are mapping it to WX, which is itself a collection of images, right? It's this filter bank, right? So intuitively, you are creating a lot of redundancy, right? There's many coefficients that you are creating, and so it's to be expected that you can reconcile. But here, basically, what it means, right, in this equation, is that we can actually reconstruct in a way that is stable, right? Like if you think in terms of a linear transform, right? This is basically just saying that as a linear operator, the singular values of this linear operator are well conditioned. They're all between 1 minus delta and delta. Okay. And so in that sense, you can also see, right, that wavelets coefficients thus complement the average, right? So remember that in this representation, right, that I just described here, this decomposition is the low pass filter that we studied before, concatenated, augmented with all these filters, like all these convolutions from corresponding to the wavelets, right? And so what this thing is saying is that if I design the wavelets in the right way, then this representation complements, right? I mean, like the information that I'm adding is recovering what is lost by the low pass filter. Okay. So this means, this going back to the previous story, right? We saw that the low pass filter was all nice. It was not sufficient, right? It was throwing too much information. So can we now combine the information that is recovered by these wavelets by our invariant, by our average, right? So basically, can we question, can we simply concatenate W with an average to obtain the invariance? What do you think? So we just draw the picture. We had our image X. We know that if we do this low pass filter, we get something that is like a stable. That's good. And now I'm basically telling you that there's all these other images that are created by different wavelets that complement the low pass filter. So how can we take all these images and extract invariance? So how can we extract invariance from here? Extract the invariance. Can we simply just pass them to our low pass filter to get stable? What do you think? So in other words, if I have X,
you keep the high frequencies again, no?
So if I have this, maybe, and then I apply a low pass filter, right? What do I get? Well, like in the extreme case where I just do the average, right? So let's say that I just do like translation invariance. So I just look at the average of X involved with epsilon. Remember from the Fourier characterization, this is just the Fourier transform of this convolution related at 0. Right? So this is just the average of the signal times the average of the Fourier transform at 0. So the average of the wavelet at 0. It's like the Fourier transform of the wavelet at 0. So, okay, so this is the same as 0 times sine of 0. And remember, what did we say that was the property of the wavelet? What does it mean? What does this property mean? That was like the vanishing moment, right? What does this thing imply? So this thing implies that, of course, the wavelet cannot produce directly new information by simply concatenating it with the average, right? Because as you know, this is exactly the same as the, so basically by construction, the vanishing moment means that there's no information. The average of the wavelet is 0, right? So the average of anything that is convolved with the wavelet is also 0. And this is really not a detail, right? It's like a, it's almost by design, by construction, right? If you think about what happens here in this equation, right? In this equation here, if I look at what happens for psi equals 0, right? If I look at this equation for psi equals 0, of course, all these terms are going to be psi of 0, right? And so because this sum is infinite, right? If this thing was not 0, if the Fourier transform of the wave of one wave at the 0 was not 0, then this thing would blow up, right? So you really need to have like a vanishing moment, which means that this thing is always going to be like this. So, but this is really, I mean, this is actually also consistent with what we said before, is that obviously it has to be, there cannot be, this cannot produce new invariants, because concatenating a wavelet convolution with a low-pass filter is still defining a linear operation. And we just saw that there's no more linear operators that are invariant other than the average. So what we need is basically to introduce a nonlinearity, right? We need to take all these wavelets and apply a nonlinearity. And so, for example, we can introduce, so we need to introduce a nonlinearity before concatenating with the average. Okay, so for example, we can consider the modulus. Okay. So if now we look at the instead of averaging or summing over the wavelet coefficients, we are averaging over the modulus of the wavelet coefficients. Okay. Now this is of course going to be non-zero in general, right? For a lambda. So now there's a instead of being a okay, so now this is of course a completely different story, right? And this is really where we want to go. I might okay, so I might just present one last result before we wrap it up, because I won't have time to do much more today. And then maybe next Tuesday, we are going to continue with the sketching. But let me just state the main property here, and we are going to resume it where we left it today. So what we need now is to really understand, that now I'm hopefully I have convinced you that if I take these wavelet coefficients and I apply this pointwise nonlinearity, I might be able to extract to obtain new information from the signal. But in that particular case, of course, it's going to be invariant to translations, right? I can create invariance by just averaging the result, right? And so, of course, if I look at this quantity, right? Let's call this phi of x, right? So phi of x, let's assume that it's just the integral of, let's define it like this, right? For all lambda, right? So fact is that phi is translation invariant. Why is that? Well, because because we know that that this operation, right, W, answer with W is equivalent to translation, right? In other words, for lambda, the translation of x involved with any wavelet is the same as the translation of x with the wavelet, right? Just by definition of a convolution. And so once I have this property, and I know that the integral of dv of y, right, u is equal to the integral of u for y and for all. Right, so I have obviously the translation invariant it's automatically derived from the equivariance, right? So basically, in other words, since W commutes with translation, W composed with the Lopez filter is invariant. As J goes to infinity, right? In the limit where I have just the average. But from what we said, this is just only one part of the story. What is important for us is not just translations, right? What we care about is near translations, deformations. So we know that this wavelet filter bank is equivariant to translations. That's because this is just because it's a convolution filter. But how about near translations? So what is interesting, what is the key property here, that is the thing that is kind of underpinning the scattering representation, is that when I replace, so basically in other words, W times T of V of X is equal to V for all X and for all. Now, of course, you can ask the question, well, if somehow this picture was true not only for translation, but for deformations, then I would be in business, right? Because I know that the Lopez filter is stable to deformations, right? So if we also had the W of the deformation of X was equal to L tau of W of X for all X and for all tau, then we would be okay because we have already seen that J of X, which is just a low-pass filter, is stable. Okay, so just to continue with the story, right, is that if I compose an operator that commutes with some group with some transformation with an operator that is stable, the composition is stable, right? But the point is that, so this is not something that we can have in general, right? Just because there's no, the group of diffeomorphisms is just too big, right? We cannot have something that is equivalent to all diffeomorphisms, right? That's something would be a good exercise for you to prove. But in fact, it turns out that we have the next best thing, right? So exact commutation to diffeo is not possible in general, but wait, let's satisfy the next best thing, okay, which is that if I look at the error, right, like the commutation error, so, and this is like a theorem was proved in 12, is that there exists c bigger than 0, such that for all j and for all tau, the norm, so if I look at the wavelet decomposition associated with scale j of this deformation minus L tau. This is basically controlled by some norm. I'm going to just put it here because it's informal, but something that looks like the deformation metric that we taught before. Okay. For some appropriate modification of the cost of all right. So basically, that's a very different thing, right? So I know that any choice of filters would commute with translations. But here, we are showing that in particular wavelet filters, they are doing something much more powerful. They are almost commuting with things that are almost translations, right? And this is like a fundamental property that really requires the multi-scale structure of physics. So, okay, so I guess that this is kind of where I want to culminate it today. And so for next week, next Tuesday, we are going to build a scattering representation from these properties. And then discuss natural extensions, which are basically the CNNs, the convolutional neural networks, and also like the graph neural networks, which are extensions to a more general domain. All right, and I think that that's going to be basically the last lecture Tuesday, and then on Thursday, next Thursday, we are going to basically wrap the whole class course by maybe discussing some open directions, like open problems and future directions. So I'm gonna stop here, and then next week we are gonna record a resume at this point. Any questions before we close it up? Okay. Anyway, so I'll see you on Tuesday, and the Tuesday I think that the time is again changed, right? It's at I believe it's at 2 p.m. So let me just check. Right, it's at 2 p.m. your time. Bye, everyone. Bye bye.